This video is going to give you a step-by-step process for developing the large watershed hands-on example that's used during the WASP workshop. We're going to focus on data management, which is a critical portion of modeling a large-scale system like this. Keeping your data organized in a format that you can readily review and use is very, very important. We'll give you a brief overview of the LSPC watershed model. We'll review some of the key model inputs, and we'll execute the model. After executing the model, we're going to actually use a couple of tools to process the LSPC model predictions into a form that can be used by the WASP model. The first tool is a post-processor spreadsheet tool, which will open up and read the LSPC output files, do proper units conversion and calculations to put the LSPC data into a form that is more compatible with WASP. It'll also export some comma-separated value files that we'll read into the water resources database. So the flow of this sort of looks like this. We'll take LSPC runs, we'll process the output data in a spreadsheet that'll take care of putting everything in the proper units, and then we'll pass it on to the water resources database, which is a database management system which makes it very, very easy for WASP to query data from WRDB when it begins its simulations. Okay, before we start to run models and processing data, let me just give you a quick overview of the watershed that we'll be modeling. We're going to be using the EPA Basins tool to restore a project that will allow us to look at our model domain in a geographical information system. Okay, at this point we're going to assume that you've installed the Basins program. If not, you'll have to install the Basins program before you move on to this next step. With Basins installed, you should have a shortcut up on your desktop that says Basins 4.1. If it's not there, you can actually click on your Start menu, go to the Basins folder, and launch Basins 4. What we're going to do is we're going to restore an archive project that I've already created with our information in it. So we won't need this screen, but we'll go up to File, Archive Restore Project. We're going to look for our archived project, which is going to be in C, WASP course, examples, watershed, basins, and you'll see this Ambrose River Basins MWA, which is the archived project. We're going to say open. We're going to restore it into a directory called WASP course, examples, watershed. And actually, I think the best thing to do is to put it back into our basins directory, just so that we know that it is a basins project. So I'll just navigate over to there. Say OK, and then click Restore Project. And it's going to, it says it's been successfully restored, so we'll go ahead and open it. So there's our project. Alright, so just to give you a brief overview, let me just shut off some of the layers. I'm going to the only layer I want to leave loaded right now is the LSPC subbasins. These are the delineations of the subbasins for our watershed. And they each have a subbasin ID, which starts with the 6 number. So for every one of them, for every one of these subbasins, there will actually be an output file in LSPC that we'll have to process. Then we have our riverine system. This is our WASP network. There's a total of 34 segments that run up into several different tributaries. The main stem starting from 15 all the way down to the lake is Ambrose River. Starting from 21 down to the lake that comes into Ambrose River, that's Wool Creek. And then 29 down to Ambrose River is Martin Creek. And then the small tributary down towards the lake is Flippin Creek. And our lake down at the bottom is called Lake Sarah. So what we'll be doing is we'll be linking the LSPC result predictions into the WASP network, and we'll go through that in a second. The other thing that I want to just show you is that we do have some point sources in here. We have Ambroseville Wastewater Treatment Plant, Wool Industries over here, and Martinville Wastewater Treatment. We will also have to bring these point sources into our water quality model. And then lastly, we have some monitoring stations in our model network that we'll use to calibrate the model. We have two on the main stem of Ambrose River up here and down here, one on Wool Creek, one on Martin Creek, and then one in Lake Sarah. So that's pretty much what our system looks like. So we're going to be processing data from LSPC. We'll also be processing point source data that we actually do in a spreadsheet that we feed into WASP via WRDB as well. And then when we get to our calibration process, we'll be comparing model predictions in WASP with our monitoring stations that are located here. Let's begin by looking at some of the components of a watershed model. The main things that we have to think about when we're linking watershed models to a receiving water body model is there are two different sources of flows and loads that come off of the watershed that have to be processed for the receiving water body model. First is land surface components, which basically is made up of sheet flow. So just imagine this is water flowing across the land surface coming directly into a river network. And that we call this sheet flow, and it's in the watershed models, it's typically in acre inches per day. And there's also a pollutant contribution that comes directly into the river network, and that's in pounds per day. This sheet flow and pollutant load adds flow and pollutants to the connected reach, or the stream network that's actually within that watershed. And this represents both the flow and pollutant contribution from the individual subbasins. The next component are reach components, which for all intents and purposes for us this is the riverine network. The reach carries flow from upstream reaches in cubic feet per second and carries pollutants from the upstream reaches in milligrams per liter. So basically, you know, if you have a reach all the way up the top, that's actually what's coming in from the sheet flow. But as you go down your model network, the reach network actually carries the pollutants from the upstream reaches as well. So we have to be very, very careful when we do the linkage. So just to give an idea of what I mean by the two different types, this is our watershed that we're going to be simulating. And there's going to be, you'll see a little bit of everything in here. But if we look at our subbasin 698, we'll see that we actually have a reach element because all of the sheet flow in that subbasin will actually enter into the reach at the very, very top. So that all the flow coming in would be in cubic feet per second and pollutant loads in milligrams per liter. Then if we look at 699, this will not be a reach. This will be actually a pero flow. So it'll be all the sheet flow from that area, and that's in inch acres per day and pounds per day. So kind of think of it this way. So the pollutant loads coming off of 699 would be all distributive. We'll actually enter that into one WASP segment, but it's all of that contributes into the reach. And LSPC accumulates these flows and loads into each reach and transports them downstream. The next thing we're going to do is I'll just give you a brief demonstration on running LSPC. I'm going to provide you an overview of running the LSPC model. We're currently in the WASP course examples watershed LSPC folder. You'll see that there is 3 files and a folder in this directory. The first file is the .air file or air file, which is the meteorological information that gets read by LSPC at runtime. This file is a simple ASCII file that is in a plotgen file format. And the information that's contained in here on an hourly time step is precipitation, potential evaporation, air temperature, wind speed, solar radiation, dew point, and cloud cover. And basically there's a line for each day, month, year, hour on this file that gets read at runtime. So that's how the meteorological file looks like. The next file is the LSPC model itself. And then the watershed.inp file is the input file that we will run to provide the flows and loads for our example watershed that we're running. And then there's a directory up here called current. That's where the LSPC result files will be written out. So let's go ahead and run LSPC. Just double click on it. This is what the LSPC interface looks like. It's fairly simple. It allows you to change a lot of different parameters quickly. Sometimes you're not able to change some things in here, so you'll have to do it outside the model. So we're going to go ahead and open our Watershed INP file. And what that's saying is it's generating the F tables for our stream network. There is a couple of particular things that you have to pay attention to in LSPC. LSPC does not allow spaces in either the directory names or the file names that it's going to read in. So we're just going to check and make sure that everything is okay in our simulation. So I'm going to go to Watershed Information, Weather Data, Data Location, and you should see C:\WASP_course examples Watershed LSPC. Notice that there are no breaks in there. If you installed LSPC or the course materials in another directory, you need to make sure that this is changed to that directory. And then the last thing you have to make sure that's changed correctly is the location of where the output's going to go. So again, it's just going to go into that current directory. So with that, we're going to go ahead and run the model. We just click on the Run button, and the model will take off and it'll run. It'll give you a dialog box that looks like this. Okay, the model's finishing up and it's writing its results into that current directory. So once it's finished, I'm going to close LSPC, and if we go into this current directory, we'll see that there's an output file for every one of the subbasins that we are simulating in our watershed. If we open up one of these files, again, it's just a straight ASCII file that's in that plotgen file format. And just like the meteorological data, this is the information that is written out, and by position here is where it is in what column. So we can, you'll see how we process this with the spreadsheet, but we also can look at the LSPC output by using the WRDB graphing program. And I would just basically open up a data file, browse to this current directory, select one of the out files. So now it's loaded all of the LSPC basins in that directory, and it shows you all of the different output. So if we wanted to plot the runoff flow for subbasin 698, we would select it, the runoff flow, add it to the graph, and that gives us the time series plot of the predicted runoff for 698. So the next steps we'll do is we'll process this with the LSPC to WASP spreadsheet. With the watershed model successfully run, the next thing we'll look at is processing the LSPC output into a form that can be read in by WRDB and then ultimately brought into WASP. This spreadsheet tool actually does several different things. It'll process out only the subbasins that you need to bring forward to WASP, but it'll also partition different time frames. So if you run the watershed model for a longer period than you're going to run the WASP model, it'll subdivide out the time frames. But it's going to do a bunch of units conversion needing for WASP. The first thing is LSPC flows, their reach flows are in cubic feet per second. WASP needs them in cubic meters per second. The pero or the sheet flow coming off are in acre inches per day, and that needs to be converted to cubic meters per second. The pero load that's coming off of the watershed also is in pounds per day, and we will convert that to a milligram per liter. The next thing is probably the most successful way for calibrating a watershed model is typically to model total nutrients, total nitrogen, total phosphorus. Usually there's not enough data to calibrate a watershed model for the individual species. If you have the individual species data, you feel free to, simulate them that way. So the spreadsheet tool will also fractionate the nitrogen and phosphorus into the individual species that are needed by WASP. So the tool sort of looks like this. It's fairly straightforward. The first tab is how you parameterize information. The things that are being circled right now show the comma separated value files that will be written out for WRDB. The station name table is basically the name of the LSPC basins and some other information. You'll see that on the next tab. The P codes are actually the parameters that are being saved, such as total nitrogen, ammonia, DO, so on and so forth. And then the WRDB data is the actual value that was predicted by LSPC. So that's sort of how it works. What's being circled now is if you're simulating total nitrogen and total phosphorus, this is how you would fractionate the different species out of the total. So if we look at the nitrogen series, 6% of the total nitrogen would be ammonia, 34 nitrate, 60% dissolved organic nitrogen, and in this case, no particular organic nitrogen. I usually typically get these ratios from looking at areas in the watershed where I have observed data, and I kind of use the average values for them. So that's how we do nutrient fractions. The next thing is, and this is a little tricky because this is how you link positions in the LSPC output file to parameters that you want to process and write out to WASP. So we'll look at this on the next slide. And of course, the button here runs a VBA script to create the WRDB import files. So this is how you map information in, and we'll look at an LSPC output file during the course. But basically, you're going to map by position. So the output's actually in rows. So in our case here, total nitrogen is going to be 25. So you can see that it's the 25th element, 22, so on and so forth. So we map these out by position so we know where they're at. And then the next thing we need to do is on the LSPC output tab, we have to say which output files we want to process, whether that we want the reach information or the sheet flow information. Reach is RO, sheet flow is PARO. We're going to assign it a station ID. We give it a station name, and if you want, you can put the latitude and longitude in so we can actually plot this stuff inside a GIS system. And we'll talk a little bit more about how important it is to name this information. So these are the files that we're going to be processed. It doesn't have to be every output file from LSPC. The PARO RO is the type of output you want processed, whether it's for the reach or for the sheet flow. And then the stations table is what's passed on to WASP. So what we really need to do is we need to be able to know, and we define which segments are flows and our reach information, our PARO information is going in. So we basically assign a WASP segment to each one of these types. So if we look at 698, we see that that's an RO, and everything that's coming out of 698 is going to go into WASP segment 15. And then if we go look down at 699, all of the sheet flow and pollutant load for that subbasin is going to come into 13. So we're kind of assigning them together. So we have to go through this whole process. And you have to be, in the end, you have to make sure that you have everything mapped in. And if you accidentally map a reach, an RO, in where there is a PARO, you'll make a grave mistake, because what that RO has in it at that subbasin is all of the subbasins upstream of it. So in this case here, I'm just making sure with the arrows that I have all of my subbasins. They all have an arrow associated with them, and the RO ones are all begin at a terminal end of the network, and all the PAROs are blue, and they are in a middle reach. So next we'll just look at a quick little video that shows us how to use the tool. Alright, after giving you the overview on how that spreadsheet tool works, we're going to go ahead and load the spreadsheet, which is LSPC to WASP XL SM, which is in the WASP course examples Watershed WASP directory. This spreadsheet does contain macros, so you may in fact have to look at up on the top of your toolbar to enable security on this, because a lot of system settings will block you until you say turn on or enable macros, like it says up here. So I'm going to say enable content. So quickly we'll just go through the spreadsheet as we live as we went through the PowerPoint. Here are our WRDB stations. They are going to be written out in the same directory that the spreadsheet is located in. And here are our assignments from the LSPC output to the variables that we want to process. This sets our fractions of the total nitrogen that goes into the ammonia, the nitrate, the dissolved organic nitrogen, and particulate organic nitrogen pool. And the same thing's true for phosphorus. If we click on the LSPC output tabs, you'll see that these are the files that we're going to process to take LSPC output. These are the types of flow types because we need to know which types they are that we're going to be using so we can do the appropriate units conversion. And then lastly, here's the station information that's going to be passed on into WRDB. So to run the macro, we'll just click and say process LSPC. It'll take a second to run, and now it has created these 3 files. So I'm going to leave here, and you'll see that those files are right here. So we have to pull these into WRDB. So our next step is we're going to create a WRDB project. Next, we're going to take the output from the LSPC to WASP spreadsheet tool, and we're going to import it into WRDB. So there'll be a step-by-step video that shows you how to use this option. Okay, we're ready to build our WRDB project. To load WRDB, go to your Start menu, All Programs, and find the program folder that says Water Resources Database 6.0, and we will load the Water Resources Database 6.0. And this is what the main screen of WRDB looks like. You may have some other things show up here, like an introductory, so on and so forth. If you click OK through, you'll get to this point. And what we're going to do is we're going to create a new project. Now what WRDB is it's just a database management system that is specific to the needs of managing water quality data, prepping data to go to water quality models and watershed models. So the first thing we're going to do is we're going to say create a new project. So we'll go File, New Project. We're going to give it a name, and we'll call this Watershed Example. And this is just the database used for the WASP course Watershed Example. And once we get here, we have to pick the different, there's different data types that we can use. These are the database file formats that WRDB supports. The first one being Microsoft Access. If you have SQL Server, you could use that. Oracle, you could use Firebird embedded, MySQL if you have it. But we're just going to use SQLite. And we're choosing this because this is the file format that we're going to use. And we have to create the blank file in a directory. And what we're going to do is we're going to go to our WASP course examples watershed WRDB directory, and we'll call this is just the name of the file. We'll call it Watershed, and we'll say open. You can put a password on here. We're not going to do that. We are going to have to create a master table, even though we'll probably not use it, so we'll just call it master. So just click on the create button, say OK, click out of here, and then just say OK. So this thing here is telling us, hey, you're about to initialize a new database file. None of the support tables are there. Would you like me to create empty ones? We're going to say OK. So we're at the point now where we have a blank database, and we're going to import those files. So the first thing we're going to do is we are going to open a working table, and we're going to say create new, and we're going to call this LSPC current, which is our initial watershed model that we set up. So this is the current condition watershed model, when we can keep track of that. The next thing we're going to do is we'll close this working table. With this one open, we're just going to go to edit, import, and then import a data file, and we're going to browse to WASP course examples watershed WASP, and the first thing that we're going to import is the stations CSV file we just created in the spreadsheet. So we say open, And everything is pretty much mapped in here to go in correctly, and we'll talk more about importing as we go through the workshop. We'll just hit continue. This thing here says, hey, what you're trying to import doesn't have any real data with it, so I'm assuming it's going to go to into a support table. We'll say OK. This table will pop, this little dialog box will pop up. You hit continue, and it says, hey, I'm going to add 14 records to a support table. You say yes. So now if we click on this green box up here, support table, you'll see that we pulled in from our spreadsheet the station information that was on the LSPC output tab. So that's our station ID, our station name, and we have latitude and longitude. So that came in successfully. So now we're going to go ahead and we're going to import the P codes. So we'll go to P code. Same thing, it automatically knows what everything is. Just say continue, OK, continue. So now we're going to pull in 13 records into the support table. So now if we click on support table and click on P codes, you'll see that we have all of our parameters in here. The P code, code, the analysis name, and the units. So that's good to go. And then the last thing is we need to bring in all of that time series data that we process for every one of those subbasins that will ultimately get imported into WASP. So edit, import, import data file. Now we're going to get the direct current. And again, everything lines up the way it's supposed to. So we would hit continue. And then it'll import information into the system. This will take a little bit longer because there is a lot more data here. So there was, if you look right here, there was 199,472 points pulled in. We click OK. You'll now see the data is being read in, and it's going to be put into this working table. This will take a little bit of time, but once it's in here, it'll be displayed. So now we can do several different things, and we'll learn more about this as we go along. But if we just want to check and make sure everything is all right, we can click on Output, Reports, Summarize by Station and Parameter Code. We're going to tell it to select all of the data from this table, and we end up with a table that looks like this. So this shows you for each one of these stations, the station name and the P codes, the number of observations, the mean, the min, the max, and the period of time that we've got processed. So that's pretty much how we import that information into WRDB. We'll be doing a lot more with WRDB, and there'll be a couple of more of these videos. Okay, our next step is to process the LSPC meteorological data into WRDB. We're doing this to ensure that the water quality model has the same meteorological conditions as the watershed model. The nice thing about this, all the data has been collected and processed at least into a form that we know for use with the watershed model. WRDB supports processing the LSPC air files as well as HSP FWDM files natively, so we don't have to do anything special other than to open up the files. We do have to do one step in the import process from the air file to WRDB for use by WASP. We do need to do some units conversion changing. The first thing is we're going to pull in air temperature from the LSPC air file, and LSPC temperatures in degrees Fahrenheit. We want it in degrees centigrade. Wind speed is in miles per hour. We want it in meters per second. Solar radiation is in Langleys per hour, and we need to convert that to watts per meter squared. Dew point temperature is in Fahrenheit. We need to convert it to Celsius. Cloud cover in LSPC, the cloud cover range goes from 0, no cloud cover, to 10. In WASP, it's going to go from 0 to 1 for a fraction cloud cover. So the next step we'll do is we'll go back to WRDB. All right, we'll switch back to our WRDB project, the watershed example. This is where we left it off. To get ready to import the LSPC air files, we're going to close this working table, and we're only doing this to make sure we don't accidentally pull it into the wrong table. And then we're going to click on Working Table, and then we're going to say Create New. And in our case here, we're just going to call this table Metadata. You'll notice I'm putting the underscore in the file names because database tables do not support spaces. And we'll just call this metadata from LSPC. And we'll close this form. So with this table active, we're going to go to Edit, Import, LSPC Files, and we're going to navigate to WASP Course Examples, Watershed, LSPC, and we're going to pick our air file. Now you'll be giving it an input form. If there was more than one meteorological station in that air file, you could pick and choose which ones you want, or you can bring them all in. The next thing we need to do is we need to go into the parameter screen and pick the parameters that we want. WASP is not going to need any of the rainfall or potential evaporation, but we are going to need air temperature, wind speed, solar radiation, dew point, and cloud cover. And you'll see that the appropriate units conversions are there. WRDB does have some built-in units where you can come over here and you can pick, in our case, English to metric, and we can go Fahrenheit to Celsius. And it will put in the appropriate conversion factor. Some of the other ones, if it's not built in, you just basically put in a multiplier, and when it brings in the value, it multiplies that value to convert it. So as an example, cloud cover in LSPC is from 0 to 10, but WASP needs it from 0 to 1, so I'm just going to multiply it by 0.1. The 0.44704 is the conversion factor from miles per hour to meters per second. The last thing that we'll do is you can set the date range. So if you had a meteorological file that was much larger and you only needed 1 year out of it, you can set the ranges that you want. And this is the range of our simulation period from 2006 to 2012. So I'm going to click OK. And you'll see down here, down at the bottom, it's starting the import process. And this will take a second. So I'm going to pause. OK. It's processed all the data and it's come back and it said, hey, there's one station and 5 parameter codes that are going to be added to the support table, and that's what we expected. So we're going to say OK, and it's actually reading the data now into our working table. And once the data is in here, we'll be able to, just like we did with LSPC, we'll be able to see the data. So here's our data. And it'll show you that we have hourly data for our station for each one of the parameter codes. So that's how you import the air file data into WRDB that we'll later bring into WASP. Okay, we're ready to start to process the point source data and get it ready for WASP. What we're going to do is we're going to pull it into WRDB to put it in the data table so that it's easy to link into WASP. We have our point sources in our watershed, Ambroseville, Martinville, and Wool Industry. These are each individual spreadsheets that have the monitoring and reporting data in it. I'm going to open up Ambroseville just to show you how the process works. And these are the constituents that we're going to actually be pulling and putting into WASP. And it's kind of important to note that the worksheet name where the data is at is prescribed here. All of this information out here in the light blue is calculated. So if I go to the ammonia tab, this basically shows what form the data has to be in, and it's in date, time, value, and you can see that it starts in 1997 and it finishes up in 2012. So it's just, they have to be in this form. And what we do is we just create a comma separated value file. In our case, it's going to be called ambroseville.csv, which we'll pull directly into WRDB. We're going to set the start and end time, so we'll only process the years that we need. So it's pretty simple. You would just build these forms, these worksheets, and put the data in there. Press the build CSV file, and it's done. And this actually gives you a summary of the data that it found, showing you the mean, the min, the max, the starting and ending period, so on and so forth. So that created that file, and we would do this for Martinsville and Wool Industries, and that'll have the data available. Okay, now we're ready to import the point source data that we processed with the spreadsheets for Ambroseville, Martinville, and Wool Industries. Just like we did before with LSPC, we're going to close this file, or that table, and we're going to create a new one, and we'll call it NPDS. And we could just say this is point source data from spreadsheets. And then we will be ready to import. So we'll close the working table dialog box, and we're going to pull data into here. So much like we did with LSPC data getting input, we're going to go edit, import data file, and then we're going to browse to WASP course examples, Watershed WASP, and we're going to pick on our CSV. So I'm going to pick wool industries first. You'll see that WRDB automatically recognizes everything, and we'll continue on. And it's just saying we're going to append that data in. So that takes care of wool industries. We'll do it again. This time we'll pick Martinville, hit continue, and that's pulled in. And then the last one we'll pull in Ambroseville, so it's edit, import, Ambroseville CSV. So that brings that data in. Well, before we move on, I want to do a little bit of cleanup in our support table so we're not confused going forward. So I'm going to click on the support table tab, and I'm going to just come in here, and this is our station for, this is our LSPC Met station. This is our point source for Ambroseville. So this is Ambroseville wastewater treatment plant. We actually have the longitude of that if we want to put it in there. It's 30.771 minus 84.462. And then we'll come down here, and this is Martinville wastewater treatment plant. And it also has a latitude and longitude that we can put in, and you'll see that this is useful later when we look at data in a GIS sense. And then this is wool industries, and it has a latitude and longitude. So I've cleaned up everything in this table, and this is good. I'm gonna come over here, and it's kind of off my screen. I'm gonna hit apply. And then the next table I want to go to is the P codes. We do have some cleanup to do here. One, air temperature we brought in from LSPC. This is actually in degrees C. Because remember we did the conversion factor. This is BOD. This came from the treatment plants, and that is in milligrams per liter. Cloud cover is intense. This is degrees C. This is in watts per meter squared. And this is in meters per second. So that cleans up a lot of the stuff that we have. So let's hit apply. So that pretty much takes care of getting all of the data in that we'll be processing into WASP in the upcoming steps. Before we leave the WRDB project, there's one thing that we probably need to do that'll make the querying of the data from WRDB tables into WASP a little bit quicker, and that's adding some indices to our tables. I'm just going to close our last table, our metadata, and I'm going to click on this Explorer tab, which is basically the same thing as going to File, Explore Database. And I'm going to click on our LSPC current table, and I'm going to click on Manage Indices, and I'm going to turn on an indice for station ID and P code. And what indices do is it provides a quicker mechanism for databases to extract information, because they, by looking at the indexes first, you can find what selected records are or meet that particular, in our case, station ID and P code. I'm going to do that for all three tables, just so it makes it a lot easier and a lot quicker when we go over to WASP. And this is just a relatively simple thing to do, but it's going to save you a lot of time when WASP is querying this data out. So with that, as soon as this is done, we're good. Our indices are created and we're ready to move on. Okay, we're ready to start building the WASP input file, and we need to load the WASP program, and we can do it a couple different ways. It created shortcuts on your desktop if you asked it to, or you can browse to where it was installed. In my case, it's E:/WASP8, and I can click on wasp.exe, and that'll load the WASP interface. What I'm going to do is I'm going to take you through the step-by-step process for building the Watershed input file that we'll use in the course example. First thing I'm going to do is I'm going to say this is a new file, so it basically initializes the WASP interface. You'll see some icons are grayed out. That's because prerequisite data has not been entered yet, so that the information can be put into those screens. So one of the first screens the first screen you have to go into is the data set parameter screen. And we're going to be using the advanced unification model. I'm just going to call this our Watershed example. And then just to keep track of where we're at, this is the initial setup. And then the first thing we have to do is we have to set the time domain of the model. In our case, we're going to go from 01/01/2006 at 12 a.m. to 12/31/2012 at 12 p.m. So that sets the time frame of the model, and keep in mind all the data that we've processed from LSPC encompasses the same time frame. The last thing we're going to do is we're going to set the model output interval, and we're going to set that to, we're going to output 4 times a day, so that's the output interval is 0.25 days. The next step is we're going to insert the state variables that we want WASP to simulate, and we're going to insert about, I think it's 17 or 18 of them, and we basically pick what we want. So we're going to pick ammonia, nitrate, dissolved organic nitrogen, inorganic phosphorus, dissolved organic phosphorus, dissolved oxygen, and we'll insert 3 BOD groups, and when we go back to label these, I'll kind of explain what they are. We're also going to insert 3 phytoplankton groups, and then we're going to go on to simulate particulate organic carbon, nitrogen, phosphorus, total detritus, solids, and then water temperature. Now the nice thing about the interface, it actually allows us to label these. So I'm just going to call this NH3, NO3. I'll call that DON, DIP, DOP, DO, and this is going to be called Watershed BOD. So that'll be the BOD that's coming in from the Watershed model. This will be called point source BOD, because we'll treat these differently in the model. And then this will be biotic BOD, which is BOD created by phytoplankton diet. We're going to call this the spring algae. This is one of the assemblages that we're going to be simulating. We'll call this one summer algae, and then fall algae. This is POC, particulate organic carbon, particulate organic nitrogen, particulate organic phosphorus. This is detritus. This is solids. And this is temperature. So that's basically the state variables that we are going to simulate. Okay, next we're going to put in our segment information. So I'm going to say OK on this screen, and we're back to here. I'm going to minimize this screen a little bit, and I'm going to go ahead and I'm going to load from our course notes the segmentation screen that has the information that we need for putting information in about segments and flow paths. So that's in the WASP course examples watershed directory, and we have this spreadsheet that has this information in it. So I'm gonna try to split the screen here between these two. Which will allow us to see where I'm getting information from and putting it into WASP and from the spreadsheet. So the first tab we're going to work on is the segments tab. There's a lot of information in here, but the first thing that we're going to do is we're going to tell WASP that we have 34 segments. So we're going to click on the segments tab, and we're going to get a dialog box, and we're going to insert 34 segments. So there's our 34 segments. The first thing I'm going to do is I'm going to come over here and I'm going to copy the segment names. Now you'll notice that there are no spaces in the segment names, because if there is a space in the segment name, WASP has an automatic parser built into it that will try to actually parse data out and pass it into another column. So I'm just going to copy that from there. I'm going to come over to segment 1 and I'm going to paste. So that gets our segment names in there. The next thing that we need to do is we need to set what kind of transport mode is going to be used for each one of the segments. The default is flow routing, but we're actually going to be using kinematic wave and ponded segment. So I'm going to go down to the bottom and I'm going to start setting these things to kinematic wave. And if you just click on it and make it blue, if you type K, it's going to set it to kinematic wave. But every time you hit the K, it's actually doing a filter and it's finding the next version of K. So the way these forms work is when you're in this mode, if there's a pick list in there, you can pick the value by the first letter. Or if you double click on this, you actually get a pick list that you can go down and pick individually and then move on to the next one. So you can do it either way. The quickest way, of course, is just hitting the K. But you can experiment with that to figure out what works best for you. And our last, or our first segment, or the bottom of the system, is our lake. So this will be a ponded weir segment. So that pretty much defines everything we need for setting the systems. If we had initial conditions, we can actually put the starting concentrations of each of the state variables on this tab here for each segment, for each system. We're going to start at 0. We'll let the model work its way to that. So that's pretty much all we have to do for segmentation. Okay, our next step in the process is we're going to have to put the channel geometry in, or segment geometry, into WASP. To do that, we're going to click on the flow screen, which is this icon here. And you'll notice that we'll have a screen that has a set of rows and columns that pretty much line up with what's in this spreadsheet. Just something about this screen, depending upon the flow type that you pick back on the segment screen, will determine whether or not information is needed for that particular flow type for a segment. So if it's grayed out, that means it wasn't needed. So like for kinematic wave, bottom elevation isn't needed. That's needed for the dynamic flow simulation. But for the ponded weir, we don't need slope or we don't need roughness either, because it's just a flow routing system. There is no wave calculation in there. So what we're going to do is we're actually just going to cut and paste our values from our spreadsheet into our WASP input file. And first thing we'll do is we'll copy the length and the width. So we would just highlight that, copy it. On the first cell that you want to paste, you paste it in. Then we're going to go ahead and we'll do slope, minimum depth, roughness, and initial depth. We'll copy that. Now I realize I did not pick up the lake. That's because some of this data is not required for it, and then I would paste it in. and I would set the minimum depth for the pond at 2, the initial depth at 5 meters, and then we'll just slide out here to the right a little bit, and the last thing that we need to do is put in the depth multiplier, which is this column here. Copy it, paste it in, and then lastly we're going to go all the way out to the right, and we got to set the weir height. This is the weir at the outlet side of Lake Sarah, and it is 5 meters, and that's the type of weir it is. So that pretty much sets our segment geometry. So we'll move on to the routing. All right, we've defined our number of segments. We've given the geometry for each of the individual segments. Now we have to go into the transport screen and actually connect these up. So this is all going to be surface water, so we're going to click on the surface water tab. And the first thing that we need to do is we need to go ahead and define how many different flow paths we're going to be given to WASP. So a flow path, basically, if we look at our network, we're going to define a flow that comes in at the top of Ambrose River that goes from segment 15 all the way down to the bottom, Lake Sarah, which is segment 1. Wool Creek goes from 21 all the way down to 1. It comes into Ambrose River at 6. Martin River comes down starting at segment 29 and enters Ambrose River at segment 5. Flippin Creek starts at 34 and comes into 3. And then we have all of the distributed flows, the Pero flows that I'll show you how we're going to add them in a second, as well as our point sources. So first thing we're going to look at is we're going to go ahead and we have Ambrose River, and this is actually the flow paths from one segment to the other. So we have to put that in. But what I want to do to make it just a little bit easier for us is I want to go ahead and I want to insert our flow function names just so we can remember what they are, and we'll call this Ambrose River. We'll call this next one, and I just hit the down arrow to do this. I'll call it Wool Creek. Then the next one is Martin River. And the next one is Flippin Creek. So once we have that, what we have to do is we're going to tell WASP basically water's coming from outside our system, which is designated by a segment 0, or in the interface it's actually going to call it a boundary, and it's going to go from 0 to 15, 15 to 14, 14 to 13. Basically we're just saying, hey WASP, we got flow coming in from outside the 15, 14, and we're routing it all the way through. This way it knows where the water's coming from and going to. And we do that by coming down here into the segment pairs screen. So I'm going to squeeze my screens just a little bit more so you can see. So we're working on Ambrose River first. So we'll hit a bunch of inserts. In our case here, there's quite a few. Now the best way to put this data in is if it's a number greater than 10, what you want to do is you just want to double click here and type in the number. Now what I'm going to do is I'm going to go down and put all of the 2's in first. So I'm going to just do this column. So it's 15, 14, 13, 12, 11, 10, 9. Now once we get down to these guys, we could just type the number just like we did with the kinematic wave. I could just type 8, 7, 6, 5, 4, 3. Now I need to insert some more. 2, 1, and then one more, because we have to have the water go out the bottom. So this now I'm going to froms, and I'm just going back up from the bottom back up to the top, and you'll notice that I'm putting this value here just to show that the water is being completely routed through. So now we're back into the 10s. I'm going to double click. It's a lot easier. So that pretty much gives us our complete path, starting from the top to the bottom. And you have to make sure that these are correct, because if you mess this up and you'll break the continuity and flows, you'll have some segments where the depths will be going to infinity and some will be going to 0. So it's kind of critical. So we're going to do the same for all of them. Okay, I have completed importing the other ones. We're going to go on to Wool Creek, and basically it's this flow path here. It's defined from starting from a boundary 21 all the way through 16, and then it enters Ambrose River at segment 6. And I did the same thing for Martin, starting up at 29, and it went all the way down. It comes into Ambrose River at segment 5, and I did Flipping Creek as well. So that's our main stems that are coming in. We'll look at how we get the flow data in after we link our WRDB project into this WASP input file. Well, we put a good bit of information into the interface right now. It's probably a good idea that we click OK here, and let's go ahead and save. This way, if anything happens, we can recover from where we're at. So we're going to hit Save. We're going to go to WASP course, examples, watershed, WASP, and we'll call it watershed.wif. So just type in watershed.wif and hit save, and that pretty much will save it. You'll see that the file name is up here. So now we're going to continue on with entering in the other sources of flow and loads coming in, but we're going to put the flows in first. So we're going to go back to the flow screen onto the surface one. Okay, the next set of flows that we're going to put in are these singular flows that are coming into a point. We have all of our parallel flows from the watershed model, which are basically the sheet flow coming out of a subbasin going into an individual segment, as well as putting in our point sources like the Ambroseville wastewater treatment plant comes into a segment 11, Wool Industries comes into 16, Martinville comes into 26, and we just have to put these into the model. Now these will each get their own individual each own individual flow function, because they have their own time series associated with it. So what we'll do is we'll come in here and we will just go ahead and come over here. I'm just going to hit the down arrow until I put in enough here, and I'm going to go back up and I'm going to label them, and I'm going to call this first one, I'm just going to go in order. I'm just going to call it LSPC 699 Pero, and you can't cut and paste into these. I'm not quite sure why, but don't do it. It'll cause a problem. Ambroseville wastewater treatment plant, LSPC 60105 Pero. All right, I completed adding all of these, so they're basically in order, starting from LSPC 699 Pero all the way down through LSP 60110 Pero. The next thing we need to do is, just like we did for the routing, we just need to route this into our model network, and it's really simple because all we have to do is just hang them off of this network that we put in. So we would just insert, and this would be a boundary to 13. This would be a boundary to 11. So basically Ambroseville is coming into segment 11. This will be to 7. Okay, I completed putting all this in. I'll just review for it real quickly. As you can see, as we move down here, you'll see that I have attached these to the appropriate segments as we go all the way down. And we'll go through how to put the flows in shortly. If you accidentally insert a flow function like I did here, you need to make sure you delete it. I'm going to say OK and save. Okay, continuing on, you can close your spreadsheet file. We don't need it anymore. And once we put the flow information in, WASP has a lot more information to build the other parts of the interface. And one of the big ones that was just built is the boundaries. The boundaries are anything that's coming from outside our system to inside our system. And in our case here, this would be all of our LSPC subbasins as well as our point sources. And you can see that they've all been discovered in the interface, and it discovers this information from the transport screens, whether you are using the flow screen like we just did, or you were linked to a hydrodynamic linkage file. All of that information would provide where the boundaries are. So what we're going to do next is we're going to actually load up and link our WRDB database to our WASP input file so that we can start populating some of this information. So to do that, we're going to click on the database linkage screen, which is this one right here, external data sources. We're going to add a database, and we're going to call this one LSPC because we're going to be using our LSPC data first. The database engine is going to be SQLite. If you remember, that's what we used to create our file in WRDB. So we'll select that. We're going to call this our LSPC connection. And now we have to just go browse to where our WRDB file is. And if you remember, we put it, when we created the project in WRDB, in WASP course examples watershed WRDB. So this is the file that we want. So now we are linked to this SDB file. Now we have to find the table. And now there are a bunch of tables that are in our WRDB project. Most of them are support tables. But one of the working tables, we created actually 3 working tables. The first one was the LSPC current, which is our current calibrated LSPC model. The next one was our meteorological data, and the other one is our point source data. So the first one that we're going to do is we're going to do the big one, the LSPC. So we're going to select that. Because we use WRDB to create these files, WASP already knows how to link the data in. You don't have to use WRDB, but you could use your own SQLite or your Access database if you want, or even a spreadsheet. But I find it a lot easier to do it this way because all of your data is definitely organized in a fashion that'll work with WASP. So the first thing we're going to do is we're going to do a parameter mapping. And this basically is going to let us map WRDB parameter codes to WASP state variables. So these are our state variables. You remember we inserted these systems and we gave them names. And when we pick on this pick list, this is actually all the P codes that are available in our LSPC current table. So the first one we're going to line up is ammonia, nitrate, dissolved organic nitrogen, and we're going to do this all the way down through the bottom. And what we're doing here is we are saying anything in that table that is called one of these P codes, it actually gets mapped into our state variable in WASP. So we're going to map the watershed BOD into watershed BOD state variable. We won't map in any of the point sources of the biotic. We did not simulate algae with LSPC, nor did we do any of the particulate components. We did do solids, and we did do water temperature. So we would bring that in here. So that pretty much maps all the state variables LSPC into WASP state variables. The next thing we're going to do is we're actually going to map WRDB stations to WASP segments. Now, one of the things that I did that makes this thing a whole lot easier is I actually named my WASP segments to be consistent with the station ID. So basically it was looking at the table that we used in the LSPC to WASP spreadsheet tool to create the file. And it basically shows us that we have linkages between, or it automatically maps them because the station name and the segment name are the same. So everywhere that we have a yellow line, that's where we have a boundary condition. And you can see that everything is mapped in, which makes it really, really nice. The only ones that aren't mapped in is our wastewater treatment plants, because that information is not in this table. With all of our LSPC stations and parameters mapped in, the next step we really want to do is we want to go back over to the boundary screen, because if we have a single data source, a table of mappings of P codes and station IDs to WASP segments and parameters, it's relatively easy to map these into the interface. So we're just going to close out this thing. We'll say OK. And then we're going to go over to the boundary screen. And you'll notice that when we come in here, it has our boundary sources LSPC, and they are all already mapped in for us. So for every one of the state variables that we're simulating, that we're getting information from LSPC, they're already here. So that kind of makes it a lot simpler for us to do all of this. So this basically just shows where our data is at. So the next thing we're going to do is we're going to go ahead and map in the point sources. All right, what we'll do now is we're going to go ahead and add another external boundary. And again, it's always a good idea to hit save as you go along. So now I'm going to go back to the database screen. I'm going to say add, and I'm going to call this one NPDS. So this is the point sources. It's the same SQLite configuration. Actually, we can use the same configuration here and then browse to our WRDB table, which is in the WASP course examples, Watershed, WRDB, and we're going to pick up our watershed.sdb file. And now we're going to go down to the point sources, so which is the working table is NPDS. And we can do the same thing. We could go into the mapping screen and we can go ammonia, nitrate, dissolved organic nitrogen, inorganic nitrogen, organic nitrogen, DO. And now for BOD, we're going to map it into the point source table. That's this one, BOD. And I think the only thing left we have here is temperature, because we've mapped all this other stuff in. We'll look at flows later. So we'll pick on temperature. And we say OK, and then we can go to stations and we can go find our point sources, and we can select Ambrose pipe 1, Wool pipe 1, and Martin pipe 1. And we're done with that. So now we'll go over to the boundary screen. We'll click on the boundary screen. Now we're going to come over here. Because there's more than one source, it will not auto-link these in because it wouldn't know which one to link in if there was a dual mapping. So really all we need to do here is click on Ambrose. If you double click and you just type NPD, hit N, or if you select NPDS, it'll go and get ammonia for that segment from the database. And then we can do the same thing for nitrate, DON, DIP, DOP, DO, and then point source. And then the last one that we're going to get is the water temperature, which is out here. So that brings in the temperature. Then we need to go on and do it the same for wool industries. Same thing, click here, choose NPDS, and the data is loaded in. Now you don't have to use the database linkage WRDB. You actually can, from a spreadsheet, just like we cut and pasted segment information, you can paste the time series data in here. It's just that we have so much of it here that it would be very, very difficult, or it would take a lot of time to do. And then the next one would be Martin. And we'll do the same thing, select NPDS. Whoops. And if you double click on the cell and then hit N, it'll stay right there where it's at. Oops, this is a none. This was a mistake. This should be none. I just set it back to none. And then lastly is temperature. So we have actually successfully linked all of this data in here. I mean, this is, thousands of records. So that pretty much takes care of putting our boundary concentrations. We could review real quickly just to make sure that everything is in there correctly. Lake Sarah is our downstream boundary, so we don't need anything because the flow doesn't reverse. We are not providing any information for the biotic stuff. We will need to set the algae boundaries to like 1 just so that we have some seed values there. And we could do that in a second. And then it just shows you that we have solids, loads, and temperatures coming in as well. So to set the algae, just so that we have a seed concentration, we're just going to put in 1 microgram per liter. All right, we're going to set the boundary concentrations for the algal components to 1. This way we have some biomass to start growing when the conditions are right in the system. And to do that, we would just click on the cell that's associated with a boundary and each one of the algal components, and we would set this time series to 1, which basically says for our whole time period of simulation, any flow coming in at this boundary will have a algal concentration of 1 microgram per liter. And we're going to go, we have to set all of these to that. So we'll just copy this row by highlighting the cell and then hitting the copy, and then just go down to the next one and insert and paste. And we have to do this for all of the boundaries for algae. All right, I've completed setting all of these to 1. We could just review real quickly. If we just click on any one of these cells, you can see that I set the boundaries to 1. The only ones I didn't set to 1 were the wastewater treatment plants. So that pretty much gets us ready for all of our boundary concentrations are set. Well, as we did before, we should go back and we should save this. The next thing we're going to do is we're going to actually bring in the flow time series that we need for each of our flow functions that we defined in the flow screen. So to do that, let's go to the flow screen, click on surface flow. So what we're going to do is we're going to pull all of the flows for our headwaters and our wastewater treatment plants from our data sources. So for Ambrose River, we know that that's going to be, the data source is going to be LSPC. The P code is actually going to be flow. And the station ID will be this one right here, of course, LSPC 60098 RO, which is there. So that just pulled in our daily flow for that boundary. Now we'll do the same thing for Wool Creek. That's going to be a flow as well. And this is going to be 101 RO. So we'll find 101 RO, and it's linked in. Then we'll do Martin River. And this will be flow. And Martin River is 103 RO. And then we have Flippin Creek, which is also flow, and this is going to be 109 RO. So this should take care of all of our ROs of where we have reach, flows starting our network. The rest of them are going to be paros or wastewater treatment plants. So the next one is going to be a paro. So we'll go LSPC flow, and then this is 99 paro. Now this one is a wastewater treatment plant, and that's not in the LSPC table, that's in the NPDES table. And again, we want the flow. And this is Ambrose, so we'll pick Ambrose. Then we're back to an LSPC table. So LSPC flow, and we want 100 paro. So you pretty much get the gist of how this works, and let's go ahead and complete the table. Okay, I completed filling out the form, and you can see that I have assigned each one of them based on the table type for LSPC, and I made sure that they line up with the segment that it's coming into, so everything's lined up. Same thing with the point sources. It's all loaded in there correctly. So that takes care of the flows. And again, you didn't have to use the database for this. You could have actually came in here and cut and pasted these values right into the input form. It's just a little bit easier to do that. And I just wanted to show you another functionality that we have in the interfaces. You can actually undock this graphics, and you can actually, get a better look at what's going on in there. So just make you aware of that. To undock it, you just click on that little icon in the upper right hand corner. All right, the next thing that we're going to do is we're going to go ahead and bring in that meteorological data that we linked to before. We're going to click OK here. Again, it's a good idea to hit save. We're going to go back to the database linkage screen. We're going to add yet another form, and we're going to call this metadata. The database engine, again, is going to be SQLite because that's our WRDB. We're going to use the same connection. We're going to browse to that database. And you can use different tables or different database files. It's just totally up to you, but it's in the Watershed WRDB directory. But now the table we're after is metadata. Now metadata may have some stations associated with it, but when it comes to WASP, there's no way to link them in. So we're not going to worry about linking them in. We're just going to connect to that table just to make it available. So for the next thing is we're going to put in these environmental conditions that change over time. If you remember, it was like air temperature, wind speed, solar radiation, dew point, and cloud cover. So to account for it in here, we're going to click on the time function screens where we're going to bring that data in. So this is the time function screens, and we're going to pick and choose the ones that we're going to use. We're not going to use water temperature because we're going to be simulating it. We will have to set the fraction daily light. This is the photo period for the day. We're going to set it to 1, which basically means it's light all day long, except that when we bring in our time function, it'll have a dark period, the nighttime period in it, and it's an hourly radiation. So we're going to bring in solar radiation. We're going to use the first one. You'll notice that there's 4. Another one that we're going to bring in is going to be air temperature, wind speed, cloud cover, and dew point. Now we need all this information so the model can actually not only provide light for algae to grow, but also it's needed by the temperature model. So just like we did in the flows, we're going to come over here and we're going to select our data source. In this case, we're going to pick metadata. The information that we want here is solar radiation. And we really only have one station, so there's our solar radiation data. It just got pulled into the interface. And then we'll go down to our air temperature. Same thing, data source, P code, air temperature, and then the station. And then we'll go on to wind speed, metadata, wind speed, station. Dew point, same thing. And then cloud cover, which I accidentally skipped over. And that will map in all of our meteorological time functions. So we're going to click OK, and we're going to hit save. Okay, our next step in building this WASP input file is we're going to go into the segment parameter screen, which is this icon here. And we broke the segment parameters out by functional groups. So the ones that we're actually going to be interested in right now is going to be the environmental condition ones, which are basically we're going to tie in the time functions that we just pulled in. So the first thing is you can have a multiplier for segment temperature, for air temperature, which basically means you can have it change temperature slightly based upon the time functions. We won't be doing that, so we're going to be setting both these to 1, and I'll explain in a second what it means, but I'm just going to highlight, the first row here, and I'm going to go all the way out to the right and highlight the second row so that I have both the air temperature of the segment and a pointer to the time function, and I'm just going to fill, and I'm going to set this to 1. Now what this says is that when WASP is updating the air temperature for each individual segment, it'll take this value here, 1, and look at the time function that we just put in over there and multiply it by that time function to come up with the air temperature. So the air temperature over our whole model network is going to be the same for each segment, but it's going to change as a function of the time function that we put in. The next one we got to do is we have to do the same thing for solar radiation, because we could scale and assign different time functions to it, but we will just pick, it'll be just 1. The multiplier will be 1 and the time function will be 1. So it's fill calculate 1. Then next thing we'll go on to is we're going to do the same thing for wind speed, cloud cover, dew point, and we'll set all of these to 1 as well. You have to be careful when you're using this to make sure that you are getting all your segments and you didn't leave it slid one way or the other. And I'll do the fill calculate, and I'll set it to 1. And I think that pretty much takes care of everything that we need to do here. So all we're basically doing is we're telling WASP which environmental time function to use for air temperature, dew point, cloud cover, so on and so forth, and if we wanted to put a scale factor on it. If you didn't want to use a time function but just set a constant value, we could have set the air temperature up here to 25 degrees and not pointed to a time function, and the air temperature for the whole simulation would be 25 degrees. So that's kind of how the parameter time functions work. We'll be revisiting these as we start turning on kinetic information. Okay, again, we just put some more information into the model. It's a good idea to hit save. The next thing we're going to do is we're going to select the information we want written out to the WASP simulation output file. WASP doesn't assume anything is going to be outputted. So we'll click on this icon here, which is our output control, and you'll see that there are functional groups. So the things that we're going to turn on, the first one is we're going to turn on mass check. I think it's a good idea to have this on all the time. Basically, if the model is running stable and everything is okay, the answer should be 1 or 0.99 something or 1.00 something. So it's important to turn that one on. We're going to put on volume, flow, segment temperature, water temperature we're going to output because we're going to be simulating it. And then that's probably it for rate for the initial setup. So we'll go from transport to nitrogen. We'll turn on ammonia. We can't do anhydrous ammonia because we're not simulating pH right now. So we'll turn on nitrate, DON, and then total nitrogen. Then we'll go on to phosphorus. We'll turn on DIP and DOP and TP, so it's going to write this information out when the model's simulating. We're not doing silica, BOD. We can output our individual sources, but ultimately in the end we're going to be interested in the total BOD, which is the sum of the number of BOD groups that are being simulated. Then we'll go on to dissolved oxygen. We'll want the DO outputted. That's the instantaneous. We can also get the daily average, which will also output, and we might want to put out the reaeration rate that's being calculated because we might want to look at it. Then we'll move on to phytoplankton. There's a lot of information here that we want. The first thing is we're going to want total phytoplankton because ultimately when we compare it to measurements, that's what we'll see. Then we'll write out the concentrations of each of the phytoplankton groups. And we'll probably leave it at that for now. During the hands-on session, I'm sure that we'll go through a lot of diagnostics on what else to look at. Let's see, the next one is going to be solids. We're probably going to write out calculated light extinction, and then probably, I'm sorry, I'm in the light group. We're going to write out light extinction. And that's probably, well, we'll turn on each component of the light extinction, the background, the algal, the solids, and the DOC. We need to keep moving on in here. We'll go to solids. We'll just write out the total solids concentration. and then temperature. I think we're going to get all we really need out of just getting the water temperature, but there's some diagnostic stuff here you can look at. So that ultimately sets up the output. So we turned on the information that we want. Again, it's a good idea to save. The only input we have left to do really is we would need to set kinetic constants, which are done in this screen here, but and they're broken out by functional groups, and depending upon what we're simulating, information will be there or not. In our case, we're not doing macroalgae, so you wouldn't see any constants there. You would only see them for the ones that we're actually simulating. And we're going to get back to that in a second, but let's make our initial run without any constants. So to run the model, you just basically click on the WASP. And what's happening right here is it's querying the WRDB database, and this could take a little bit of time depending upon the speed of your machine and how fast your hard drive is, because it's pulling in probably almost 2 million records from that database, which includes all of our boundary conditions, our flow conditions, and our meteorological conditions. So, and once the data is pulled in, the model will take off and running, and that's what it's doing right now. So what's up on the screen? These are the current predictions of the model. So this is pretty much a conservative calculation of everything that's going on, except for DEO, because it is not conservative. And we also have some, on this screen here, we actually get some initial feedback from the model, which also includes the version number and all of that information. And if any issues there were with the input file, they would be described down here. And then lastly, down here on the bottom, you have the meter that's showing how far we are in the progress. And then you also have a date timestamp to show you where the model is at in time. And if you saw something that wasn't quite right here, you would click on this cancel button, and it would shut the model down appropriately so that you can look at the output file. But as it progresses through time, it's writing information out to that output file 4 times a day, because that's what we told it to do. Upon completing, it'll go through a process and it will close the BMD file, and then ultimately when you say OK here, you're back to where you can edit again. So one of the things that we need to do, because you'll be looking at the output file a good bit, is we're going to go ahead and create a project, and we're actually going to add the output file to the project so that when we go to the post processor, it automatically knows where it is. And that's going to be in WASP course examples Watershed WASP, and it's going to be called watershed.bmd2. BMD2 file extension is the file extension that indicates that it's a WASP output file. With that, we're going to say OK. We'll save it because that's going to actually get saved part of the WIF. So now when we go to the post processor, we would just click on this icon. Okay, what happens when you click on the post-processing icon? It requires that you have the water resources database installed, which I'm certain we have at this point because we used it to generate all of our time series. So this graphing tool is actually one of the utilities that comes with WRDB. And because we built our project file, when we came in here, it actually loaded up all of the data. So just to give you an overview of it, here are all of our segments, by their names, and here are all the output variables that we actually selected. So if we wanted to look at the advective flow coming in at the top of Ambrose River, we can go find the where it comes in, which is right here. We can look on the map and see that. But if we select the segment and we select the parameter and we say add to the left axis, there is the flows that came into our segment. So we can look anywhere in our model network and look at what was predicted by the model. So we can click on and we can come over here and say let's look at coming down Lake Sarah. Let's look at the total nitrogen coming down the Lake Sarah, and we can see it changing through time. So it allows us to plot anything we want. It also allows us to plot, we can plot, we can go to Lake Sarah and we can plot water temperature. We can add that on the left axis. and then we could add dissolved oxygen on the right axis so that we can see the relationship between temperature and dissolved oxygen. And you could tell what is what by looking down here on the legend. So that's the graphing tool. There will be separate webinars on using all the functionality of the WRDB graph for doing calibration and generating reports. I just have to give a quick shout out to the person that's responsible for WRDB and WRDB graph. I have worked with this gentleman for 20 some odd years now. His name is Dr. Chris Wilson. He works. He has his own business called Wilson Engineering, and we have worked together for some time to make this a very, very good tool for not only looking at ambient monitoring data but also modeling data as well.